Am I audible in the back? Yeah. So what were we doing in the last class? Okay. Someone says Mux architecture, someone says pages. We started with ROM cells. What kind of ROM cells do we have? We looked at two kind of ROM cells, NOR ROM cells and NAND ROM cells. And we saw that NOR cells were optimized more for speed, whereas NAND cells were optimized for density. Why does it not start? This is a little strange. हाय मैं A007 से बोल रहा हूँ यहाँ पे टीवीज पे ठीक डिस्प्ले आ रहा है उस पे सेंट्रल स्क्रीन पे नहीं आ रहा है एक बार आप आ जाएंगे थैंक यू Yeah. So we looked at two kinds of ROM cells, NOR ROM cell and NAND ROM cell. And we saw that independent of whichever way you would program them, whether you were programming them on the source or on the drain. I'm audible in the back? Yeah. Whether we are programming it on the source or on the drain side, or whether we are programming them on the contact or via, we saw that both have different flavors and different kind of benefits that one can draw from it. While on the NOR ROM cell, there was a large variation in capacitance that you could expect if you would program on the drain side, that is on the bit line side. In the NAND cell, those current variations can anyways happen depending on how many ones are stored or zeros are stored inside your one ROM cell. So when you're talking about ROMs, you have to always take care of these systematic variations which can happen. What do we call as systematic variations? Variations which you can model, variations which you can anticipate, variations that you can take care of by design in your verification itself. In a later chapter, in a later section on mismatch, we will look at these variations, that is systematic variations, and we will also look at random variations. Those are the variations which you really cannot do nothing about. Okay. So this was about the NOR ROM cell and the NAND ROM cell. Then we started to look at the IO circuits, where we looked at precharge. Now, what kinds of precharge did we look at? We said that the most basic naive precharge type would be static precharge. Am I right? Where we said that this the PMOS is always on, and even when your word line comes, this PMOS in a way mitigates your differential that is intended to be created. Are you with me? So what was the alternative to that? The alternative to that was that we would put a clock at the pre-charge gate. What would this do? Yes. So when the clock comes, and for us, word line is also a kind of a clock because it is triggered by the clock. It is derived or it triggers only when clock comes. Signals do not influence it. Only when clock comes, you get the word line. So since for us, word line is also like a clock, when we use another clock, let us say pre-charge clock, to turn pre-charge off, then when word line clock comes, this pre-charge would be turned off. And I will be able to create differential more effectively. Are you with me? So we move from a very basic native static pre-charge into a zone where we had clocked pre-charge. Then what did we do? We added an equalizer. What was the role of the equalizer there? Yes. What the equalizer did was that even if there were a series of, just give me a second. So the role of the equalizer was that even if there were a multiplicity of cycles reading 1 or reading 0 on a particular bit line, which could have led to buildup of some inherent differential, inherent offset between the bit lines, an equalizer would ensure that at the end of every cycle, both the bit lines are at almost equal level. Okay. I'm saying almost equal level. I'm not saying equal level. Why?
Equalizer is also MOSFET, right? So if suppose we have VDD on one side, it will give VDD minus VT, or it will also have some change.
So she's saying because the equalizer is also a MOSFET, and then she added that because it has, if we give VDD on one side, it will give VDD minus VT on the other side. Sorry? It's a PMOS. So the other side will also get to the same voltage. There's no VT drop that we will observe in a PMOS. But even then, I use the word almost equal, not equal. Why? So you're saying because of leakage current. No, it's not because of leakage current.
Another part that is helping
So
the bit.
another part that could be discharging the bit line. No. Yes, it is an RC. Even that on equalizer has some resistance and the bit line has a huge capacitance. So there is an RC delay. And all of us know from our basics, first class on digital circuits, that to reach full VDD, it would take infinite amount of time. So to equalize both bit lines to 000, matlab the difference between them being 000, it will take infinite amount of time. We don't have that kind of time. So what do? We say that, okay, we will define a reset is complete when the two bit lines are within 3 millivolts of each other, or 2 millivolts of each other, or 5 millivolts of each other. That is a designer's choice. Suppose I say that I want the bit lines to converge to 2 millivolts of each other. What is the consequence?
One will discharge early, one will discharge later.
So he's saying one will discharge early, one will discharge later. No. I'm saying that I just said that equalizer will bring them to almost equal level, not exactly equal level. If that almost is equal to 2 millivolts, what is the consequence?
We have to increase the offset of the sensitivity.
We have to create 2 millivolts extra differential. We have to assume that sense amplifier has 2 millivolts extra offset. If I do it at 5 millivolts,
Extra 5 millivolts.
now extra 5 millivolts. So what is the advantage of, or why do we want to play with this 2 millivolts or 5 millivolts over there? So let us say this was my bit line, which was at 0. I had just done a write operation. And this was my other bit, which was a VDD, and the pre-charge would have gone a little low because it would start to pre-charge. It would start to conduct charge to this one, and then they will gradually converge. Okay? So what happens? If I say that I want convergence up to 2 millivolts, I will have to say that reset happens here. If I say 3 millivolts, I would say reset happens here. If I say 5 millivolts, I would say reset happens here. When I say reset has happened, I can now start to give the next clock. So when I increase the almost value, I improve timings because my next cycle can start a little early. But is it good enough? What is the concept? No, this means that next cycle will start early, तो हमेशा benefit हो जाएगा. फिर equalizer लगाया ही क्यों?
There could be data corruption. If
No, we said that an equalizer would bring them almost to same value. That almost, we have to discharge the bit line extra. So even though I recovered a few tens or hundreds of picoseconds by bringing the reset a little earlier, now I have to discharge my bit line 2 millivolts, 3 millivolts, or 5 millivolts extra to be able to do a correct read. Are you with me? Are you with me on this? So it is a trade-off now between two timings. Will I increase the access time, or will I let the cycle time increase? Abhi tak, until now, you were looking at trade-offs between timings and area, or timings and power. But as an SRAM designer, you also look at trade-off between timing and timing. Interesting. Similarly, comes when we will talk about address decoding, you will see there is a trade-off between setup and hold. Remind me to talk about it when we talk about setup times and address decoding. Is that okay? Yes.
so, the trade-off is between the cycle time and the read time.
Access time. Are you able to see this? So, see, it is not for no reason that I still enjoy designing SRAMs. There's so many tricks, so many things that you have to take care of. It's a maze. You navigate one path and a new path. You get to see, oh, there's another path from here. It's fun. It's an adventure. Every time you design an SRAM, it's an adventure. Something new will appear. And that's why it is fun. So, we are not able to get the projector right. So if you want to split into these two halves, if it helps you, please do. That's your choice. Sure. Mhm. So bitline pre-charge, even though we had not looked at this nuance last time, this is one thing that it's important for you to understand. Is that okay? Okay. And then what was it that we did after that? Column decoders. So we looked at column decoders. The first question that we had to solve about the column decoder was where to place the mux with reference to sense amplifiers and write drivers. If you place the sense amplifiers and write drivers above the mux, there's a huge area penalty. but you gain speed because the RC of the MUX, the resistance of the MUX transistors, does not come into picture of your bitline discharge or a read or write operation. Are you with me? But when you put it beneath the MUX, the sense amplifiers and the write drivers, you save area. Because now that one sense amplifier is shared across all the 4 or 8 or 16 bit lines that you ever talked about, whatever is the size of your MUX. The next thing that we looked at was uh, the type of multiplexer design. So one thing that we agreed was that when we design the multiplexer, it will be a like multiplexer and demultiplexer merged into one. We would not use logic gates to multiplex or demultiplex. We would use PTL or transmission gate logic, whichever suits us more, so that it can be bidirectional. You can multiplex and you can also demultiplex. Anyways, PTL are high density logic, and if you have to transmit as 1, you will use a PMOS. If you have to transmit as 0, you will use an NMOS. अगर आपने ट्रांसमिशन गेट लॉजिक भी यूज कर लिया तो आपका बायडायरेक्शनल मक्स बन गया. नाउ डू यू रियलाइज ऑल दैट डीवीडी के अंदर वी सेड दैट पीटीएल के अंदर इतनी सारी लिमिटेशंस हैं, ट्रांसमिशन गेट्स में इतनी सारी लिमिटेशंस हैं. वी टॉक्ड अबाउट सो मेनी लिमिटेशंस इन दीज, बट नाउ बिकॉज वी आर इन अ वेरी स्पेसिफिक सेटिंग, none of those limitations bother us. Are you able to see this? In fact, you will see that when you go to column decoder design, you will see that on the right driver side, you will have the NMOS of the transmission gate. And that NMOS of the transmission gate will not connect to the PMOS, to the sense amplifier. So it's not really a full transmission gate either. Because you know that sense amplifier only needs a PMOS. So why show extra load to the sense amplifier? Why show the load of right driver to the sense amplifier? And the right driver needs to transmit a 0. So why show the load of the sense amplifier to the right driver? So you gain speed. So the limitations that we talked about for the pass gate or transmission gate logic are not existing over here at all. Are you with me? And if you also have to design a multi-VT design, if you have the flexibility to use multiple VTs in your design, SRAM cells array, you will always use HVT. Okay? Because that's a huge array. It's a leaky place. Almost everything is not touched, no dynamic power consumed there. So you want to reduce leakage as much as possible. It is almost always HVT. Remaining circuits can be a mix of LVT or SVT. But depending on how big a MUX you can have the MUX transistors in LVT or in SVT also. Suppose it is MUX 32. Then an LVT MUX transistor may mean leakage from 31 others, unselected. So you may not want to go to LVT. So depending on MUX size, now you have the flexibility to choose which VT to use. Because otherwise, bitline to sense amplifier input might get a little delayed. So if you can go to a slightly lower VT, you can gain speed without compromising on leakage much. Are you with me? So we looked at simple simple column decoder. We looked at tree column decoder, and then we also talked about the hybrid column decoder. Okay? Any questions from the last class before we move to the next topic? Yes. I'm sorry? Yes. The way we will use it in our class, column decoding and MUX are same.
So it's not that the column decoder is a part of the MUX, like the 2-input NOR decoder.
Yes. So someone may say that the decoding of address into A bar, B bar, or the 4 select lines is the only decoding. No, that is not the decoding that we look at. That decoder you could place inside your control block also. When we are talking about I/O, we are saying that finally the implementation of connecting my bit line to my sense amplifier or write driver to my bit line, that is where the mux operation is happening. Just the control signals are being generated somewhere else. So for us in this course, or for the terminology that we will use over here, we will say column decoding and mux are same. Now to generate those control signals, you need some logic. That logic you may decide to put inside your control block because that is common to all the IOs. Are you with me?
Sir, और भी कुछ doubts थे. Sir, in the previous class we talked about this mechanism in which we do selective pre-charge off. We don't do pre-charge off for the entire array. So in that case, would it make would the column decoder design become more complex because then you have to control the pre-charge also? Separate
So
for that.
Madhav is asking that when you have to do selective precharge, that is non-selected columns will have their precharge on. So does the column decoding architecture become more complex? A column decoding architecture doesn't become complex. Precharge architecture becomes complex. So where you would be sending the precharge clock to all the devices to turn them off, in a selective precharge case, you will also use the column decoding information into that precharge block. So the column decoding information does not just go into the column decoder part, it also goes up into the precharge. That's how you have to kind of redesign the interaction between column decoder and precharge blocks.
In the last class also we talked about the hierarchical multiplexing architecture. So we talked about that we divide the mux into like we divide the pair of bit lines into two pairs. Like if there is 8 pair of bit lines, so 7 bit lines. So we split into 4 and 4 pairs. So I asked you that when do we need two sense amplifiers? There you said no, we need one only. So if we are using two mux and then both has one output, then how we are needing just one sense amplifier there?
So it depends, Arpit. We could use two sense amplifiers. Your question was, do we need? I said, no, you don't need. You could use. No one stops you. But is it needed? No, it is not necessary. After the first level of decoding, I could just have the same design as the tree decoder. And the pass gate would relay across the next stage also. Even then, what have I done? Instead of a stack of, if it was mux 8, instead of a stack of 3, I now have a stack of 2 only. But if you really want speed, you could put a sense amplifier there and then use a digital mux afterwards. Are you with me? Is this question clear to everyone? His question was that in a hybrid or a hybrid architecture that we talked about, do you need two sense amplifiers? I said, no, we don't need two sense amplifiers. But that doesn't stop us from using two sense amplifiers. Need means you have to put. No, we don't have to put. If you're not so worried about speed, you're more worried about density, you will not put two sense amplifiers. But if you're going to hybrid architecture for speed, then you will have to, because then you wanted speed. And going to a tree will reduce the speed. So it's an optimization that you have to do. You will see some designs where there is a sense amplifier there, other designs there is no. So there is no one good design. Depending on your requirements, depending on what the user needs, depending on where you want to optimize, you play.
There also one more thing in tree decoder we talked about that the disadvantage of tree decoding is there is large delay because of this type of transistors, and we say that if the project goal is speed, then we prefer tree decoding.
If the project goal is density, then we prefer tree decoding. If the project goal is speed, tree decoding will only delay, add more delays. Digital mux is using AND gates, NAND gates, and regular gates to do the multiplexing. That is how you did multiplexing in your DVD program, na? So that is digital mux. They're using PTL logic, so that I will not call it digital mux. It's an analog mux in a way. It is transmitting even very small differential from the bit line into the sense amplifier. For a digital mux, you would have to require bit line to discharge to at least VDD by 2 to say it is 0 or it is 1. That's the difference.
Some 2-3 questions related to quiz. So there was one question that what is the main function of the equalization transistor during bitline recharge? So the answer was just ensure both bitlines begin each cycle at nearly identical voltages. Why could not it be to minimize the sense amplifier offset as well? Both are same thing.
Wait. We will talk about sense amplifier just now. So we'll look at it then. What leads to sense amplifier offset? Sense amplifier, whether you put an equalizer or not put an equalizer, does it even touch the sense amplifier? Can it therefore change its offset?
But if we
How much you need to discharge the bit line, that may change. But does it change the sense amplifier offset? No.
So the option was regarding the predefined sense amplifier offset.
Whatever is the sense amplifier, uska offset. We will talk about the offset of a sense amplifier in just a little while.
One more question. There was one question that when statements correctly compare NOR and NAND ROM cells, and one of the option was NOR ROM provides predictable bitline capacitance, and this was marked ROM.
So if you do brain-based programming, then it doesn't offer.
But if we are comparing NOR and NAND, then the NOR obviously gives predictable behavior compared to NAND. Okay, it has one part, like if we are considering drain programmation, then it may be.
So yeah, I understand where the confusion can come, and that is a tricky part around it. But the intent of the question, or the intent of making this question, was that we recognize that if you do not program NOR in the right manner, the capacitance can change. But I understand the confusion. We can see how to remove that from the marks wala criteria. Okay? कितने खुश. I'm handling this because मुझे पता है यहाँ पे खुशी की लहर दौड़ेगी if I relax just a little.
It is source programming or base programming.
So you made an assumption.
Sir, one more thing.
See, I am happy with putting ambiguous questions in the quiz also. You know why? Because then it makes you think. You twist and turn your brain and say, क्यों हो रहा है? Then you come and, सब कुछ जब हार जाते हो तब आते हो क्लास में, सर ये बताओ क्यों हो रहा है? It's okay.
Sir, we sense amplifier above the mux, then it increases areas, and if you put below the mux, then it goes straight. But if we talk about driver or the writability, is not the write operation depends upon the word line arrival more than the
So we'll talk about the race conditions at the end of this chapter, let us say IO design. And it is not just that, because when abhi right driver mein we will look at the negative bit line right driver and you will see.
Because placeability doesn't affect the right operation itself.
We'll just see. So we will just see. Negative bit line aane do. Okay. So yes.
From features because it's starting in initial classes.
Okay. So thank you. She's saying that in one of the earlier classes when I had talked about, I said that ROM precharge ka mujhe yaad dilana, that I will talk separately about ROM precharge. See, until now when we're talking about SRAM precharge, we said that this is a part of reset cycle. We say that the bit line should be precharged to almost equal values, close to the desired precharge level, before the read operation starts, before the word line comes. So we have essentially just now also put a trade-off between the almost equal bit lines as a reset time or cycle time, and we have said that excess time would be after that. In ROMs, however, now why? Okay, now just let's take just one step back and understand uh, why is it necessary to keep the bit lines pre-charged for a SRAM? I'm not using the memory. I could pre-charge the bit lines even before the cycle starts. I am saying pre-charge is a part of my reset operation. So why is it important to have it as a part of my reset operation and not at the beginning of the cycle? It reduces the access time. Okay. Is that the only reason? See, in SRAMs, what could happen is that if one particular bit line has a lot of zeros or ones written on it, then the other side can actually discharge very significantly, or that side can discharge very significantly if there is no constant charging mechanism. What that can lead to is that the one that you had stored inside the memory cell can start to leak from the pass gate, which is off. That is why I'm using the term leak. And that can result in degradation of retention voltage. Okay, it's a very secondary or tertiary impact. Speed wala is a more primary impact, but that can also happen. But that impact is so strong an impact, it's like saying that आपका locker के अंदर आपने कुछ रखा था और वो गायब हो गया. So you cannot, even though it is the secondary tertiary impact, it is so non-negotiable impact that you don't want it. Okay. So for SRAMs, that data loss is something that you simply want to avoid. So you have to keep the bit lines pre-charged. Okay. Even if you discharge them, you ensure that they are somehow held at a voltage which is not too bad. Okay. Now, for a ROM, that doesn't exist. ROM is read-only memory. You can't write into a ROM now. So whatever is written is written. So for a ROM, that is the advantage, that you don't need to worry about retention. So the only thing you worry about is speed. And many times ROMs are high density. Speed is not a botheration. So what you do is, in such ROMs, you say that why pre-charge? Let the bit line leak to whatever level. It's not going to impact my contents at all. So why pre-charge? At the end of cycle. They say I will pre-charge only at the beginning of the cycle. It impacts delays a little, acceptable. But it saves power. Because if I keep it pre-charged, the bit line will continue to leak throughout the time when this ROM is even not being used. And ROMs are used sparingly. So it makes all the more sense to do it like that for ROMs. SRAMs mein aapko probably a very high density and a very low power SRAM where you do not use a 60 cell but some other kind of a cell whose stability is maintained, you can keep the pre-charge off. For example, in an 80 cell on the read bit line, you can decide to keep the pre-charge off if you know that this memory is not to be accessed very frequently. So those decisions also you can take depending on what is the use case. That can lead to further. So if you start to look at, so there was this assignment and we said that you should read papers as a part of those assignments. So if you start to look at all these nuances that I'm talking to you about, it could help you deepen your insights, and the project titles that you have to propose, you could do them not the routine bit cell design, but you could go a little more interesting, replicating something that someone else has done and published a good paper, something like that you can do. So if you're looking for papers or something like that, I would say choose the best conferences or the best journals. Don't go for tier 2, tier 3 conferences, go for ISSAC, VLSI Symposium. VLSI Design is also okay. ISCAS, CICC. So these conferences are. And in terms of journals, look at TCAS 1, TCAS 2, JSSC. You can look at TVLSI also. So look at these 3 or 4 journals, those 4 or 5 conferences. That's a good place to find interesting papers which could help you uh, identify some nice projects for yourself also. Okay. So any further questions? Yeah.
The bit lines can discharge into leakage, and that can cause that corruption of data because the one stored inside one of the cells, and there's the bit line and it is discharged. So it can actually leak to the basket and change the data inside the cell.
It will weaken the stability of that one because the PMOS is already the weakest device in the memory cell, and it can result in a data loss. The retention voltage can suffer. If we do pre-charge at the beginning of the cycle, at the reset of, yes, you can do. You can always reset the ROM, like you can include pre-charge in the reset path. That is the standard that I just shared. I wanted to share that for ROMs, you have an additional flexibility and you can use that also. Standard to aap kar hi sakte ho. Why not? Okay, anything else?
So in the quiz, there was a question. What is practicality failure that both modes perform simultaneous write-off? So, but two read writes, it would not be possible to do two writes at the same time, right? The controller should.
So it's not about two writes on at the same time on the same cell, actually, Ria. Because the 2 word lines are on. One word line is on because it's writing in the adjacent cell. Another word line is trying to write into you. So in that situation, write operation starts to suffer.
So the correct answer, one of the correct answers is that there's a short circuit condition.
Yes.
So
The short circuit condition because you did a selective pre-charge off on the other bit line, other port. So you were not doing anything on my particular column. So the bit line pre-charge was on. That short circuit path from that bit line pre-charge through my pass gates into the write driver of the port. So there are 2 ports, port A and port B. Let's talk about port B. Now port A was writing on the adjacent cell. So for the cell on which port B is writing, it is an unselected cell. Its pre-charge is on. So port A's pre-charge for the cell selected by port B has a short circuit path into the write driver of port B. So, this is closer to you, easier to see. Let us say this is port A, and let us say this is port B. There is a write driver here that wants to discharge this particular cell. Okay. And from port A, there is this pre-charge that is charging this particular cell. So between this bit line and this bit line, so BL A and BL port B, let us say, there is a series of one pass gate that leads to the latch and the other pass gate that takes away from the latch. And then there becomes a short circuit path through these pass gates from the pre-charge of port A to the write driver of port B. And now in that short circuit path, you're not able to take this internal node to 0. Because this is again a kind of a potential divider forming in. Potential divider from VDD of port A to ground of port B. Because port A, the same word line was on, and the precharge for only this adjacent cell was turned off. The precharge for unselected column of port A was on. If I had blanket precharged off, then this path would not have existed. Are you able to see this?
So this specific condition exists only when port A is reading, right? So one read and one write off.
Port A could be writing,
Then the
but on the adjacent cell only, na? It is writing on the adjacent cell. You can't put a condition on port A. Port A and port B completely asynchronous हो सकते हैं ना? But for that particular cell where you are facing a problem, yes, port A is reading in the read mode. Not exactly, not even it's not even reading, it's in a read mode. The word line is on. If it was reading, the precharge would have been off. Even then the problem wasn't there. Are you able to see this? So now we come to the next heavy topic of this course, which is the sense amplifier. We've been reading about the sense amplifier, hearing about the sense amplifier for so long. So what is a sense amplifier?
amplifies the differential between the bit lines.
It is a small amplifier that picks up a small differential between the bit lines and amplifies it between 0 and 1. Why is it needed?
Increase power consumption or increase
It is needed in read operation, yes, but why?
the speed of the cell faster.
Because the bit line capacitance is very large and our mem cells are very, very small. With a large bit line capacitance and a small memory cell, what happens? The small memory cell will take a lot of time to discharge that long capacitance. So if we do not have a sense amplifier, if we want to have a digital 0 or a digital 1 or a digital mux at the output of my bit line, then it would take a lot of time for the bit line to discharge to below VDD by 2. Now, if we want to speed up the memory, we would rather somehow use an amplifier where a small voltage discharge can be quickly read as, let us say, 0. Are you with me? So that is about speed. But then I also heard the term power. Why does it, how does it reduce power also? Yes. Now, all the bit lines, they don't need to discharge to VDD by 2 or lower. They can discharge to only a small value delta V, which could be much smaller than VDD by 2. And therefore, all the bit lines, the capacitance will now have lesser discharge, so lesser precharge power required at the end of the cycle, so you save power. Is the sense amplifier also a density enhancer?
No.
Huh? Kitna strong no aaya? Are you sure? Suppose I want a particular speed. I want a speed of 500 megahertz. I do not use a sense amplifier. What do I need to do?
So it could be a density enhancing in one case that increase by divide side.
So if I need to achieve 500 megahertz and I'm not allowed to use sense amplifiers, only option I have is either use a different kind of a memory cell which has bigger devices on the read port. So I use an 80 cell with bigger devices on the read port so that I can read very, very fast and through an inverter then. So a typical one read, one write cell in any given technology, a one read, one write cell would typically have at least 30% more area than the 60 cell. See, in 80 cell, you have a 60 cell plus 2 extra transistors which are discharging the read bit line. That is typically 30% extra area. Typically, can be 35, can be 45 also, but 30 is what generally technology offers in a vanilla flavor. You want more speed, they will go to a larger cell also, but vanilla, 30% extra area. Now, every cell, because you're not using a sense amplifier, to get that desired speed, now you need to use 30% larger memory cell. Versus use a sense amplifier and use a denser memory cell. Are you able to see this? So in those terms, sense amplifier is a very integral part of memory design. It helps us to achieve the desired performance at better density. It helps us to achieve better performance at the same density. And it helps us reduce power for the same speed, for the same density. Are you able to see this? And that is why so many people, when it comes to memories, are fascinated by the sense amplifier. You search for sense amplifier papers and you will find hundreds of them in the literature. Why? Because it plays such an important, such a pivotal role in memory operation. Now, the most commonly used sense amplifier is, so these days, yes. नहीं नहीं हम कर सकते हैं, but हम ये भी कह सकते हैं कि because I have a very large read current and the bit line will discharge fast enough, I need not use a sense amplifier. At least there's an option. In a 60 cell, if you want speed, even after desiring to have the speed, you cannot use a sense amplifier. You cannot get that speed without a sense amplifier. You put an inverter on the bit line. That inverter then controls the latch. So instead of a sense amplifier, you use a digital circuit, an inverter, for an 80 read port. Okay? You can use an AND gate. You can do a variety of things. So a typical conventional sense amplifier that is very commonly used these days is the latch type sense amplifier. Now, if you look at it, the bottom latch, it looks very similar to a memory cell. Is it not? Okay, there is one extra footer transistor somewhere there. Otherwise, it looks very similar. There's one more difference. एक तो footer transistor आ गया, दूसरा ये pass gates are no longer NMOSes. These pass gates are PMOSes. Why PMOSes?
The bit lines are recharged to VDD.
Bit lines are pre-charged to VDD, so and हम कह रहे हैं कि थोड़ा सा ही discharge करेंगे bit lines. We're not taking them to VDD by 2. So using a PMOS is good enough. Or using a PMOS is anyways desirable because an NMOS would not even react at that level. For an NMOS, there is expected to be a VT drop. So the NMOS will not change anything inside the sense amplifier if I use an NMOS as a connecting or a coupling device there. So to couple the sense amplifier to the bit lines, I need a PMOS. And even though the structure is very similar to the standard 60 cell, the design is done very, very differently. In a standard 60 cell, the layout that we saw, you realize how dense it was, so many rule violations, this, that, and sharing across cell boundaries and so on. Now, this is a sense amplifier. It's an analog circuit. Memory cell is also an analog circuit, but this is where the entire speed, power, everything is going to be determined. So over here, you design sense amplifier very, very carefully. You make a common centroid layout for a sense amplifier. How many of you have heard the term common centroid earlier? Centroid? Centroid, okay. Centroid you have. What is a centroid? Let us define what is a centroid. मतलब तुक्के मार रहे हैं.
Object could be the control. triangle के दो vertex जब perpendicular डालते हैं intersect करते हैं.
She's saying bisectors of all the three triangles of a triangle. You're saying vertical perpendiculars drop. So for us, you also heard the term center of gravity. What is center of gravity? Now that is physics. पहले math बोला, फिर physics बोला, फिर semiconductors पे आएंगे. But what is center of gravity in physics?
Body is conducted.
So the point where you assume that the entire mass of the body is concentrated, that is center of gravity. So essentially अगर आप देखो तो आप कह रहे हो there is one body, there is another body, and the two bodies can have their center of mass or their centroids somewhere associated with them. When I say common centroid now, what would it mean? Now, when I use the term common centroid, okay, I'm using it in terms of layout, but we talked about centroid. Centroid का एक essence हमें मिल गया. What would common centroid mean according to you? So, if the strength of my device could be pinpointed, concentrated at one point, then two devices are designed in such a way that their centroid coincides. फिर क्या बात कर रहे हो? ऐसा कैसे हो सकता है? So have you seen those physics problems where the centroid is outside the system, outside the physical? So metal hai, for example, think of a shell, a spherical shell. Where is the centroid? At the center of that shell. Now, is there any metal there? No, but the centroid is there. Now, can I have another shell enclosed within this outer shell and placed again such that its centroid also overlaps with the outer shell? I can. Now, physics is समझ में आ रहा है अब, huh? So now, what it means, and this is also a shell. So it also does not have any mass at that particular location. Are you with me? So that is the philosophy of common centroid, where we say that all the variations. So one thing is evident, that if this is the sense amplifier, there would be some matching that is required to have minimum offset. Any amplifier. You've seen amplifiers in your earlier courses, have you not? B may or some analog circuit course, you have seen amplifiers. Now in amplifiers, what happens is that there is this some stack of NMOSs, PMOSs placed together, and you say that I will give a very small input at one particular place. Something like this you do. And then you take output from somewhere and you say a very small differential at these two nodes will lead to a full amplification or a much more amplification at the output node. That is exactly what we are doing here. And now let us say, Arpit, जो भी आप offset का सवाल पूछ रहे थे. Suppose I said that this signal is at minus 5 volts, millivolts, and this signal is at 0 millivolts. And when I do this, the output hangs. If I take it to minus 6, it says this is 0. If I take it to minus 4, it says this is 0. सर ये क्या बात कर रहे हो? यहां 0 है, वहां -4 है, तो भी वो 0 वाले को 0 बोल रहा है. एक्चुअल में तो -4 is lesser than 0. But that exactly is what we call as offset of a sense amplifier. Two devices were intended to be matched, but at the time of fabrication, One device had a little higher VT. So let us say this device had a little higher VT. So you require the input to be slightly lower to get the same effect as for this device. This is so the offset of this sense amplifier or this amplifier would be 5 millivolts. That when one is at 0, other is at -5, then it is not able to resolve. To be able to put one on the other side, I have to put a 5 millivolt thing on that side. Are you able to see this? So this is what is called as offset. Now, whether you pre-charged bit lines to zero convergence or 5 millivolt convergence, that doesn't have any bearing on this. Does it have? How you design it has a bearing on that. But the sense amplifier offset is dependent on variations inside the sense amplifier itself. Now, one thing that is observed is that if I have this bigger wafer, let us say, then variations are observed like contours. Why are they observed like contours? So इस रिंग में एक तरह का VT आएगा. Why? Because see, I put a drop of my hydrogen fluoride, whichever the etching agent is, at the center of the wafer. You've seen the videos of how wafers are handled. Have you seen? YouTube पे मतलब बड़ी बड़ी मशीन के अंदर दिखाते हैं कि आपने एक ड्रॉप ऑफ केमिकल यहाँ डाला सेंटर पे, देन आपने उसको रोटेट करा, बहुत हाई स्पीड पे रोटेट करा, तो ऑल दिस स्प्रेड आउट in concentric circles through the entire wafer. So all these reagents that you use, that chemical processing that you do is actually happening in concentric circles around the center where you had put a drop of your reagent. Even the light, when you throw the light, you want it to go fully parallel, but it also, has some variations as you go a little left, a little right. So what you notice is that all the variations or most of the variations are in this manner. Now, if I put a sense amplifier, I design a sense amplifier over here, it would see that, let us say, this is transistor A, this is transistor B. It would see that transistor A has a different VT than transistor B. Let us say higher VT. Now, if this sense amplifier or if this chip was being manufactured over here, then transistor B will seem to have higher VT than transistor A. If I would manufacture it here, both may have same. So what is happening is that depending on where I am placing my sense amplifier, my offset requirement would change significantly. Are you able to see this? I already mentioned multiple times earlier that as a designer, you are a control freak. You do not want things to be changed without your knowledge. You should be able to control whatever happens. So what you want now is, अभी ऐसा क्यों हुआ? अभी ऐसा इसलिए हुआ because I could clearly say that A is here, B is here. इनका center of gravity, इनका center of mass, इनका center of strength are two separate places. Now, if I could put both of them at the same point, what would happen? It would be same variation across both. So whichever place my die is on the wafer, I don't need to bother now. See, can you change the design from this part of the wafer to that part of the wafer? No. The same mask, it will scan the entire wafer in the same way. But you will start to observe yield loss in this ring because of these variations coming in. You don't want that. So what you say is, I will do common centroid layout. Now, schematic doesn't make a difference. Finally, what goes on silicon is the layout. Schematic में आप कुछ भी दिखा लो, it will always assume common centroid. But on silicon, if you do not draw things common centroid, you could observe some extra offset requirements different parts of the wafer. Now, if you do not have timing margins in your design, then that could lead to failures, yield loss. You don't want that. So what you say is that, okay, if I have a device, let us say I have two devices, A and B. If I design them just like one finger, then A ka center of gravity is here, B ka center of gravity is here. However, if I say that where is the center of gravity of A? Here. Where is the center of gravity of B? Common. So this is common centroid in a way. Now let's check if this kind of a variation makes an impact here or not. Let's say we had, let me use the other color pen. Let's say we had a contour coming like this. We had higher VT on this side and lower VT on this side. We're assuming a linear contour. Okay. What would happen? Oh, this particular B has high VT. This particular B has low VT. Average, medium VT. Interestingly, A, both have medium VT only. So, because the centroid was same, I could get to the same VT for both the devices, effective VT for both the devices. You use any kind of contours. आप ऐसे shape में बना लो, आप horizontal बना लो, कुछ बना लो. You will notice that a common centroid will give you same kind of variations on both the devices or on all the devices which have the same centroid. Are you able to see this? So what does, अब देखो हमने SRAM सेल के समय क्या करा था, हमने कहा था शेयरिंग करेंगे, ये करेंगे, वो करेंगे. यहां पे हम क्या कर रहे हैं? We are breaking the device. Forget about sharing, we are consciously breaking it. We will make guard rings around it. Why guard rings? So that गलती से भी कहीं से भी कोई भी नॉइज ना आ जाए इसके पास. सबस्ट्रेट से चाहे गार्ड रिंग को पूरा VDD से भी कवर कर देंगे. नॉट जस्ट सबस्ट्रेट गार्ड रिंग बट आल्सो मेटल गार्ड रिंग, ताकि there is no interference, no coupling also coming. Are you able to see this? So we've thrown all those area is diamond into the air. Why? Because that area is diamond is possible only when if this really becomes a diamond. If this does not behave well, then all that story of dense, yield is lost. Yield khatam matlab, all that area is diamond is gone. Are you with me? Area is diamond is not at the cost of yield, not at the cost of functionality. मैंने कहा था ना, functionality is paramount. Area कितना भी हो, अगर आपका 6 sigma stability नहीं meet हुआ, तो that cell is no use. Stability is a functional figure of merit. For that 6 sigma yield, whatever best area you can get, that is what you have to do. So this is about yield, this is about functionality. So you say, let the area go for a toss in the sense amplifier. Okay, we still want density. ये नहीं कि अब मैं मैदान की तरह दूर-दूर बना दूंगा. I will still keep them as close together as possible. But now all that of sharing and this and that, I'm not keeping those paradigms into picture. Are you with me? This is an analog circuit. इधर offset कितना है has a huge bearing on your SRAM speed, SRAM power and overall density also. तो थोड़ा सा इसकी डेंसिटी लूज करने में हमें कोई दुख नहीं है. We don't mind. But overall system level पे it leads to gains. Are you able to see this? Now, until now, what we've done is common centroid, guard ring. But in reality, you also need to take care of how the metals are drawn. Suppose for connecting these two lines, you use metal 2. Now, how will you connect metal A? you could say, okay, I will use metal 2 like this. Now for this metal 2, first the wire length has become different. Second, they are, suppose metal 2 ki etching mein gradient tha. Now this wire will be more resistive than this wire. Okay, they are very, very close, I understand. But let us say there was another signal running from here on the bottom side. Now that signal is causing a coupling to this one, but not to that one. Are you able to see this? So when you are drawing a sense amplifier layout, you have to be super careful about everything. We call that structural matching. So common centroid along with structural matching, that every metal for node A versus node B, I also ensure that it has the similar coupling with every signal that I could have coupling with. For example, let us say sense amplifier के ऊपर से SAEN signal जा रहा है, जाएगा ही ना? The sense and amplifier enabled signal is going to turn that footer transistor on. That is going to go from there. It will couple with different devices in a different way. Now, when SAN signal is going, it should couple exactly the same way with SAT node as it couples with SAF node. So to structurally match the capacitances. I'm saying structurally match. आप खाली capacitance को equal नहीं कराना है. Structurally match करना है. Because अगर वो दोनों वायर्स एक साथ इतने दिन पैरेलल जा रही हैं तो दूसरे के साथ भी उतना ही पैरेलल डिस्टेंस चाहिए. ये नहीं कि हाँ सैट का अलग कैपेसिटेंस, सैफ का अलग कैपेसिटेंस इक्वल है. Structural matching means matching with every wire is similar. It's very difficult to achieve, but it has to be done. Are you with me? So those of you who want to do projects on sense amplifiers, I'm already telling you that start. Because the layout is going to take time. And the learning that you would get would be tremendous. How to characterize the sense amplifier. There are so many things around a sense amplifier. Each thing will take time. It's true for SRAM cells also. We looked at the 6 figures of merit. You just try to play and tune the figures of merit. So you better start to think of your projects right now as soon as possible and start to work towards them. Don't wait, because this is an elective course. We don't want to, fixate you on a certain set of projects only. You want to do something, please explore, do. There's a lot of learning in the sense amplifier. There's a lot of learning in the memory cell. There's a lot of learning in other aspects that we will cover. But whatever we are covering, you can already start to read papers, think about those projects or projects around those topics already. Is that okay? So how does the sense amplifier work? This slide has been on for so long. I've been talking everything else but this slide. Ab to bata do, how does the sense amplifier work?
Firstly, the sense amplifier is equal to 0. So the BMOS pass gates connect the bit lines to the internal nodes of the sense amplifier. Then the bit lines got pre-charged. Then word line becomes on. It discharges the bit line to a VDD minus VDD voltage, and slight discharging. Then sense amplifier enable becomes 1. The below NMOS of the sense amplifier starts taking currents from the both sides, and then
Okay, thank you. तुमने वीडियो देखा हुआ है, समझ में आ गया. But it also became evident that many of you have not watched the video in advance. Your choice. So what we are doing is that we are at the beginning, when the memory is all reset, sense amplifier is connected to the bit lines are pre-charged to VDD, everything is hunky donkey. Sab kuch bilkul hunky dory, bilkul sab kuch theek hai. Okay. Now you want to read on this particular memory. First thing you do is switch off the pre-charge. So all the pre-charges are turned off. Even for the sense amplifier, the pre-charge is turned off. Then the next thing you do is you bring the word line. When the word line comes, then depending on what is stored in any particular memory cell, bit line or bit line bar would discharge. So what happens? There is a small differential that starts to get created between bit line and bit line bar. Now the interesting thing is that SAN is 0 as of now, and SAN is the signal that is going on the gate of the PMOS is there. So my sense amplifier is closely coupled with the bit line. Whatever and this is a PMOS, so whatever little differential will come on the bit line will also translate onto the internal node of the sense amplifier. So if you're calling those internal nodes SAT and SAF, what are we calling them here? V out and V out bar. Then V out and V out bar are then practically following bit line and bit line bar. Are you with me? So there will be a little gap. Bit line will be at 100 millivolts, at say 900 millivolts. Bit line V out could be at 902. And bit line bar is at 1 volt. V out B would also be at 1 volt because of the pre-charge ke samay ka tha. So on the bit lines, you have a differential of 100 millivolts. On the V out bar, you have a differential of say 98 millivolts. A little loss would happen because we just saw that there is a pass gate, PMOS, has some resistance. Internal nodes of the sense amplifier, V out B, have some capacitance. So there is going to be some RC delay. Some loss of discharge would happen, but not much. They are PMOSs, they transmit VDD and voltages close to VDD very nicely. So we're not worried. So once we have sufficient discharge in the bit line and bit line bar, or sufficient differential created between bit line and bit line bar, we take SAEN to 1. As soon as SAEN goes to 1, what happens? First thing that happens is bit lines are now decoupled. Now the sense amplifier is on its own. Think of it as कि आप रॉकेट लॉन्च करते हो, आपने रॉकेट लॉन्च करा एंड आपने अब सैटेलाइट को उसके ऑर्बिट के पास जाके छोड़ दिया. Now your rocket has no control over the satellite. Satellite has to do all that little tinkering, moving left, right, whatever it has to do by itself now. Are you with me? So now your sense amplifier is decoupled from the bit lines. Your satellite is away from the rocket. And the sense amplifier now also has this NMOS turned on. Abhi tak it was only collecting that differential, but now with that NMOS turned on, this sense amplifier acts in a turbo mode. It now becomes active. This NMOS starts to sink current. There was a differential of, let us say, 100 millivolts between the two V out and V out bar. Let us say V out was 100 millivolts lower. Let us say V out, yahan pe kya likha hai? I don't know. Let's see. यहाँ पे SAT और SAP दिखा है ना, तो let us say SAT मतलब V out was 100 millivolts lower. Now what happens? This particular NMOS on whose gate this SAT node is going, that and this particular NMOS whose gate this SAT node is going, that will have lesser current. Are you with me? SAT is lower than SAF. So जहां पे भी SAT जा रहा है, that NMOS is going to have a little lesser current, which means that SAF node जिसको वो discharge करने वाला था, that will discharge slower. Anyways, SAF was higher. Now it will also discharge lesser. So you turned on this bottom NMOS, so it starts to sink current from both SAT and SAF. But because there was some initial differential between SAT and SAF, we now see that SAF is discharging. It was already higher level, and now it is also discharging slower only. SAT is, on the other hand, discharging very fast. Because SAF is discharging lesser, the rate of discharge of SAT remains to be very high. Are you with me? As SAT discharges more, the rate of discharge of SAF reduces further. There comes a point when SAT has discharged so much that the PMOS on the SAF side turns on. What does it do? As soon as that PMOS turns on, it pulls back SAF to VDD. As SAF goes to VDD, what happens? That SAT node, that now discharge quickly because now the NMOS is driven to full VDD. Essentially, that is what latching action is about. Essentially, that is what latching action is about. Are you able to see this? Now, sense amplifier offset हमने बात करा. The time it takes for a sense amplifier to arrive at a 0 and 1 output is termed as reaction time of the sense amplifier. Okay? And you do not measure reaction time at SAT and SAF. After the sense amplifier, you also have a latch. Why? Why do you need a latch? Because to reset the memory again, you will take sense amplifier nodes back to VDD. Then all this 0 and 1 on SAT and SAF would be lost. But memory still needs to drive the output driver. Old output has to be held until the new output comes. Is it not? So you need to latch the output of the sense amplifier somewhere. So sense amplifier reaction time is not just about V out and V out bar discharging or SAT and SAF resolving. It is about that latching the correct information. So in a sense amplifier, even though आप जहां भी देखोगे खाली ये दिखाई जाएगी आपको photo, but there is a latch that goes next to it, after it. आपको उस latch तक का reaction time measure करना है. Is that okay? And you would see that those of you who do this project on sense amplifier, you would see that if this is SAEN pulse width, okay, so SAEN pulse width is growing, then this will be the way my offset would appear to be. At a very small SAEN pulse width, offset will be large. Offset requirement will be large. What does it mean? For a given reaction time. For a given reaction time, for a very small SA pulse width, I need a larger offset. What does it mean? SAEN. SAEN pulse width, yes. SAEN pulse width, let's put it like that only. So you want a short reaction time? Your reaction time is fixed. You are saying my sense amplifier will remain on for a very short duration. In that very short duration, those V out and V out bar, whichever had to be discharged, has to be discharged. My latch should also latch the right output. There is going to be some delay. To be able to quickly differentiate between 0 and 1, I need to turn that PMOS on as fast as possible. जब तक PMOS नहीं on हुआ, तब तक मैं 1 और 0 को differentiate नहीं कर पा रहा. तब तक मेरा SAF भी fall कर ही रहा है. It doesn't go back to 1. So I want to turn the PMOS also on very fast. So my other side, SAT, should fall below VT as early as possible. So if I have a very short sense amplifier on pulse width, then I would want कि जितना close ले जाओ VT के, उतना अच्छा है. So my offset requirement has increased. Are you able to see this? If my sense amplifier pulse width was very long, I had a long reaction time available to me, then, okay, let it leisurely discharge. Finally, there will come a point when the PMOS will turn on, and then I will be able to differentiate between 0 and 1. Then my latch will also be able to operate. But if so I will now, so this then, where this thing stabilizes, is your technology driven offset. This is because of your design constraints. Are you able to see this? Now, you could draw a similar curve between VDIF and sense amplifier reaction time. If the VDIF is less, reaction time will be large, but soon it will stabilize. Are you with me? So whatever circuit you design, always try to look at trends between various figures of merit there, because through that you can optimize the design. Are you with me? Is that okay? So, sense amplifier operation. Is it clear to every one of you? But SAEN is 0, na? The NMOS is off, so it's not a latch yet. Huh? अगर ground से connected नहीं है, तो how does the ground even come? How does the 0 voltage come? Then it is just a capacitance. Latch में क्या होता है? अगर आपका ground का connection नहीं है, तो you only have a capacitance then. Look at it. There is no pathway to ground. You can only charge the circuit, and this circuit can store only as much charge. It's a capacitance. Some node will be at VDD, another node will be at VDD minus VT. All those things will be there, but it's still a capacitance. It doesn't do anything. There is no active current flowing through the circuit if the NMOS is off, if the pass gate on the bottom is off, if the device on the bottom is off. So it's not a latch at that time. You can pre-charge it. It's like a capacitance only. Is that okay? Anything else about the sense amplifiers?
In the earlier lectures, I asked you when do we make sense enable 1? So you told me that when.
So when do you want to make sense enable 1 now? What will you tell me?
Right operations.
Right?
Sorry.
See, that was what we talked about, na? Once the required VDIF is achieved, you want to turn the sense amplifier on. That required VDIF will depend on what is the sense amplifier reaction time that you're looking for, or what is the SAEN pulse width you have. Are you able to see this? These are all interlinked problems, interlinked variables. They have to be optimized together. So let us say I had a very strong constraint on SAEN pulse width. That SAEN pulse width has to be 200 picoseconds only. Let us say. It means my VDIF requirement will be this much. Until this kind of a VDIF is achieved, I will not turn my sense amplifier on. However, if there was no constraint on my sense amplifier pulse width, I would turn it on here. Where my VDIF is, I can turn it on much earlier now. Are you able to see this? So my access time could be faster because my VDIF is lower. So I could have a reaction time somewhere here. And a mix of how soon I was able to turn on my sense amplifier plus the reaction time, I may be gaining time. Are you able to see this now? So do you see there is no one fixed answer here? Again, depending on your design priorities, things would change. And do you also realize that if there were no design priorities and you had accidentally designed something like that, you want to do something else, you just relax. If you understand your circuit well, there is so much to play. It's not like कि हाँ भाई 13 tracks के अंदर आपको इतना बड़ा PMOS लगाना है और इतना बड़ा NMOS लगाना है. Do you see the game has completely changed? There is so much of design leverage here. There is so much of layout leverage here. There is so much that you can do in the design now. All this only after you know how to design those standard cells. If you do not even know how to do that, how will you do this? That's why that is a foundational course. This is a elective. But there is so much more fun over here. At least I enjoy it. Are you able to see this? So this is one kind of a sense amplifier where we had coupled. So we had coupled the bit lines with the sense amplifier through those PMOSes. There's another sense amplifier called as an alpha type sense amplifier. Okay, so this is about how to latch. So this is the latch that I was just talking about. And there is this another kind of a sense amplifier where the input nodes or the Vout and Vout bar or SAT and SAF are coupled through a capacitance, not through transistors. What is the advantage of such a coupling? Now we have separated the DC level of the bit line from the DC level of the sense amplifier. My bit line could be at 1 volts, but my sense amplifier could be operating at 0.7 volts. Why? Because sense amplifier is a turbo engine. It would consume a lot of power. If somehow I can reduce only the sense amplifier voltage without impacting the bit cell, I can reduce overall power consumption. Are you able to see that? So that is the advantage, where instead of coupling through a resistance, so a MOSFET is a resistance. Instead of coupling through a resistance, I've coupled through a capacitor. Now there is another way of coupling with a capacitor. And that kind of a sense amplifier is called as alpha type sense amplifier. Over here, I've coupled with the gate capacitance. So gate ki bhi to capacitance hai na? I've still used just a transistor, so it is denser. But I've coupled through a gate capacitance now. If you were to compare these two, what would be the difference? Why would you choose one over the other?
Associated with it, you can just devices that might be smaller.
Okay, but then why would anyone then even propose a simple capacitor-based design? You're right. Using a device or a gate-coupled thing is denser. But what is the disadvantage?
So if there's no constraint on the amount of difference that you can have between
It's stacked. The stack is now longer. There are 3 NMOSes in the stack now instead of 2. So it is slower. It's a density versus speed trade-off. Are you able to see this? Is it okay? It's a density versus speed trade-off. And okay, so another thing that you should notice over here is that in the first sense amplifier where I had used capacitances to couple, there is no precharge on the internal nodes. There's just an equalizer. So my internal nodes of sense amplifier need not be at VDD. They can be much closer to the Q point. And wherever they are not going to impact anything else because they are only capacitively coupled. There's no resistive path. There is no short circuit current that can flow. That is the other advantage of using a capacitively coupled sense amplifier. So your design can be faster. Okay. And while हमने अभी तक SRAMs के sense amplifier के terms में कहा कि there would be a sense amplifier per mux and you wanted this coupling and everything to be happen. In DRAMs, there is a sense amplifier coupled to every bit line. When we will cover DRAMs, we'll look at the reason in more detail. So just jot this thing down that when we cover DRAMs, we should look at the sense amplifier aspect in a little more detail there. But over there again, you will see latches to latch type sense amplifier is used, and it helps us to do the refresh also as we read. So we'll look into it again in some detail when we touch the DRAM sense amplifiers. Is that okay? Yeah. Any questions?
Sense amplifier is denser than capacitor amplifier. These capacitors can also be made using MOS capacitors.
No, need not be. You could make them through metal also. Depends on what you want to achieve. If you so for example, when I designed the sense amplifier, my goal was to be able to move from 0.3 volts to 1.2 volts. At such a wide range, device-based capacitances would have nonlinear behavior. For me, that was unacceptable. So I used a metal-based capacitor. You could also design those capacitances through devices. Is that okay? Anything else? So great, all the best. And I would repeat, please start to identify some interesting papers that you would want to read, or identify projects that you would want to work on, then identify papers that you want to read. It will help you. Okay. All the best.